Hey guys, I'm Craig Enders. Thanks for checking out the Blimp video channel. In this video, I'm going to talk about path modeling and mediation models in Blimp. So I'm going to limit our focus to manifest variables, and I have a different video that shows how to set up latent variable models. Before we get started, I want to thank the Institute of Educational Sciences for all their support and point you to the project's webpage. You can download Blimp at the same website. Okay, to make the illustration more concrete, I'm going to use data from an educational intervention. The predictor set includes a binary variable that indicates whether students were assigned to an intervention or comparison condition, as well as math pretest scores. The dependent variable is a math post-test measure taken at the end of the school year, and I'm going to look at models where the intervention transmits its influence via one of two mediators, self-efficacy and anxiety. As a starting point, let's take a look at a single mediator model where the intervention influences post-test scores via math self-efficacy. Here's a path diagram of the initial model along with the commands from the Blimp model statement. The model consists of two regression equations, one for self-efficacy and then one for math post-test scores. The tilde in the equations acts sort of like an equal sign in a regression equation with the dependent variable on the left and predictor variables on the right. So this looks like a fairly generic single mediator model, but I want to take a second to show you the underlying specifications so that you can kind of understand how Blimp differs from other software packages that you might have used. In another video, I explained that Blimp does not make any assumptions about the multivariate distribution of the data. Rather, the MCMC algorithm uses something called factored regression specifications. So the idea here is to take the multivariate distribution and break it up into a series of submodels, each with its own distributional assumptions. This particular model consists of three submodels. So we have two dependent variables or outcomes, self-efficacy and math post-test scores, and then there's an exogenous binary condition indicator. So looking at the syntax off to the left, as I said, outcome variables are to the left of the tilde and predictors are on the right. And exogenous variables have a special status in Blimp because they never have explicit models of their own. So if you notice in the syntax, the condition variable appears only on the right side of a tilde. So the single mediator model has a factored specification that consists of three submodels. The advantage of this specification is that each of those regression models can have effects and different types of variables that would be inconsistent with off-the-shelf multivariate distributions like the multivariate normal. A variable's role in a model actually dictates the type of metric that it can have. Exogenous predictors like the intervention indicator can be normal, binary, ordinal, or nominal, but those univariate outcomes like the mediator and math post-test scores have a much wider range of variable types that we can use. I'll talk about multivariate outcomes in a few slides, and those two have a specific range of variable types that they can take on. So to make our life easy, we built Blimp so that it automatically constructs the background models for incomplete predictor variables. But there may be situations where you want to specify those distributions or models manually, and so let me show you how to do that. So here I simply add another regression equation to the model section where condition is the dependent variable and the intercept is on the right of the equation. And this is important. I define that variable as ordinal up here, so that way Blimp will invoke an appropriate probit regression model for discrete data. So pulling it all together, this is the entire Blimp script, and I've highlighted the model commands that we just looked at. So you can find information about the other commands in different videos. Each regression equation in the model command has its own summary table. So this is the output table for the self-efficacy mediator. I described the Blimp output in a different video, but quickly, the median column contains our point estimates. The standard deviation column is measures of uncertainty, Bayesian standard errors. Then the 2.5 and 97.5 columns are 95% credible intervals, or our Bayesian confidence intervals. And then the rightmost columns, the chi-square and p-value, those are frequentist test statistics if we want them. So looking at the coefficients section, the condition estimate is positive 0.53. So that tells us that students in the intervention condition were about a half a point higher on the self-efficacy mediator. And this is the summary table for the math post-test scores. And looking at the coefficients section, the efficacy effect is positive 1.58. And so that tells us that increases in self-efficacy are associated with higher post-test scores. Next, I want to show you how to attach labels to parameters in the model. So labeling parameters has a lot of different uses. We can assign custom prior distributions, impose equality constraints, do custom significance tests. And so what I'm going to do here is label the two indirect effect pathways, the A path and the B path, let's call them. And I'm going to use those slope coefficients to compute a new parameter that is the indirect effect. So looking at the regression equations in the model section, I use the @ symbol to label a pair of slope coefficients, A and B. And then down in the parameters command, I use those slope coefficients to compute a brand new parameter called AB that is the product of the two. So at every iteration of MCMC, this new parameter AB is going to get computed by multiplying the slope coefficients from that iteration. In that previous Blimp script, I asked for 10,000 computational cycles or iterations after the initial warm-up or burn-in period. And in this graph, what I'm doing is just simply creating a kernel density plot of the 10,000 indirect effect estimates from that analysis. So you can see that the distribution of the parameter is pretty positively skewed with a long right tail. And this graph also illustrates that the 95% intervals are quite asymmetric here. And this is exactly what we want when testing indirect effects. So notice that the null value 0 is outside of the 95% interval. And so we can conclude that the indirect effect is significant at p less than 0.05. When we use the parameters command, we get a new summary table labeled generated parameters that contains, in this case, our indirect effect. The point estimate is 0.80. So the positive value means that students in the intervention condition score 0.80 higher on math post-test via that indirect effect from self-efficacy. And at the rightmost side of this table, there's a chi-square statistic and p-value, and those are essentially MCMC-generated Sobel tests. So we want to ignore those completely and just focus on the 95% intervals to determine significance. Okay, so next, let's add a second mediator to our model. The model command now features regression equations for both mediators, and I label the condition slopes A1 and A2. The post-test model, I label the mediator effects B1 and B2. And then if you look down at the parameters command, I'm computing two indirect effects, one via self-efficacy and one via anxiety. So notice that the residuals of the two mediators are uncorrelated. Condition effect is responsible for 100% of the correlation between those two variables. Now that's probably a really unrealistic assumption because efficacy and anxiety likely correlate for reasons other than condition. But I want to highlight this right now and show you how we can modify the model going forward. Familiar fit indices aren't available for factored specifications because the model parameters usually don't combine to reconstruct a multivariate distribution, right? That's kind of the entire point of adopting this framework, is that we want to introduce distributional assumptions on a model by model basis or submodel by submodel basis. But what we can do instead to assess fit is to look at residuals and residual correlations. So at every MCMC iteration, Blimp computes residuals by just subtracting the predicted scores for the dependent variable from the observed values. And then it takes the residual data matrix and performs a second round of estimation, the purpose of which is to get all of the correlations among those residuals. And those correlations can help us identify sources of association that persist after we fit our model. This model has three outcome variables, and so there's a residual correlation for each pair. The correlation inside the orange box is the residual association for the two mediators. So it's important to note that this is not the amount by which we're mispredicting their correlation like it would be in a standard SEM model. Rather, this is the correlation that persists between the residuals after we subtract out the predicted scores of each variable. Notice that the chi-square and the p-value, as well as the 95% intervals, tell us that this residual correlation is statistically significant. So this helps us understand that we have a misspecification in our model that we could remedy by adding a residual correlation. Here's the modified model with the correlated residual. That residual association you specify by separating the two mediators with a double tilde. Let's take a look at the underlying factored regression specification. So again, we're not going to make assumptions about the multivariate distribution of all four variables, but rather we're going to break the model into submodels, each of which has its own distributional assumptions and variable types. So when we specify a correlated residual, this automatically invokes a multivariate, in this case bivariate distribution. This model is actually represented internally as three submodels. We've got a univariate model for the predictor, we've got a bivariate model for the two mediators that are correlated, and then we have a univariate model for the outcome variable. The generated parameters table now has two indirect effects listed. And again, we want to ignore the MCMC Sobel test and focus on the 95% intervals. The indirect effect via self-efficacy is significant at p less than 0.05 because 0 is outside of the interval, but the indirect effect via anxiety is not significant because 0 is within the interval. Before we go forward, I want to show you a little bit of housekeeping. So every regression equation in the model section has its own summary table, and those summary tables are ordered alphabetically. There may be situations where we want to specify the order of the output tables manually, and we can do that really easily by inserting labels into the model section. So in this example, I insert two model block labels, mediator.models and outcome.model. And those just have to end in a colon. And what that ends up doing then is printing the self-efficacy and anxiety models first on the output, and then the outcome model, the math post model, would be next. This is totally optional, of course, but this helps you arrange the output in a way that makes sense to you. Now let's go back to that single mediator model, and I want to show how to add a covariate and then also an interaction effect. In this model, I'm adding math pretest scores as a covariate in both the self-efficacy model and the math post-test model. I want to again highlight the underlying factored regression specification. Things have changed a little bit because now we have two exogenous manifest variables, and those are going to share a bivariate distribution, and then the efficacy and math post-test variables are both univariate outcome models. Again, they could have their own distribution separate from the predictor distribution. The generated parameters table has our mediated effect now that we've controlled for pretest scores. And again, we want to ignore the Sobel test and pay attention to the 95% interval. Next, I'm going to add an interaction effect. So let's say that we want to know whether the effective intervention on self-efficacy depends on a student's baseline math, sort of the level of achievement that they walk into the study with. I'm going to put a pretest by group interaction in the model, and I'm going to limit that to the self-efficacy model just to keep things simple, but you could do the same thing to the B-path part of the model as well if you wanted. Okay, in the efficacy model, the interaction is specified by joining the two variables with an asterisk like I show here. When we have an interaction, it's important to note that the lower order terms are conditional effects. So the condition effect in this model is actually essentially the treatment difference for a hypothetical student who has a score of 0 on math pretest. And we don't actually have zeros on this variable, so the condition effect is essentially an extrapolation outside of the data. So I want to make a few modifications here to improve interpretability. The first thing I'm going to do is center the math pretest scores at the grand mean. And then next I'm going to label the interaction coefficient in the efficacy model. And I'm going to do that so I can compute simple slopes later on. And then the third thing is that I'm going to override the default specification that assigns a bivariate distribution to the predictors. I'm going to make math pretest scores a dependent variable that depends on condition. So essentially I'm replacing the curved arrow with a straight arrow. And the reason why I'm doing that is going to become clear on the next slide. Any variable that has an incoming arrow, any outcome variable in our model, we're going to be able to access its standard deviation in the parameters sections. This is the output table for math self-efficacy, and there's a note saying that we grand mean centered the pretest scores. So looking down at the coefficients, the condition effect is positive 0.479, but that's a conditional effect. That's the intervention effect at the mean of the moderator. Now the interaction effect is negative, so that tells us that 0.479 intervention effect decreases or gets more negative as math pretest scores increase. When we have interaction effects in our model, we often want to probe the interaction by looking at simple slopes or conditional effects at different levels of the moderator. So what I want to do is use the parameters command to compute simple slopes at -1 standard deviation from the mean, at the mean, and then 1 standard deviation above the mean. And so if you remember, I made math pretest scores sort of an explicit dependent variable. The reason why I did that is so I could access the standard deviation of the variable. And so what I'm going to show you next is how to compute simple slopes at each level of the moderator, and then use those simple slopes to get conditional indirect effects, again, mediated effects at each level of the moderator. Okay, so let's look at the first equation. This is the formula for a simple slope. So we just need to substitute in a value of math pretest, and then we can use the coefficients to get the intervention effect at that level of the moderator. And what I'm going to do here is look at the simple slope at the mean, and then 1 standard deviation above and below the mean. The first indirect effect is for students who are high at baseline on their math achievement. So notice that I'm plugging in the standard deviation value into the simple slope equation, and then I'm multiplying that by the B1 coefficient to get a conditional indirect effect. So down in the parameters command, I've appended the word total var to the math pretest variable's name. So that's going to access the variance of the pretest scores at each MCMC iteration. And then notice that I'm taking the square root to get the standard deviation. So the first line in the parameters command is simply computing the simple slope at 1 standard deviation above the mean, and then it's multiplying it by the B1 coefficient. So next we centered the moderator at the mean, so its average is 0. And you can see then that the indirect effect is just simply A1 times B1. So a coefficient drops out here. And then finally, the third line is the conditional indirect effect for someone who's low on the moderator. So again, I'm accessing the standard deviation using that .total var function, and now I'm subtracting that standard deviation to get the indirect effect at 1 standard deviation below the baseline mean. The generated parameters table now has 3 indirect effects, 1 for each level of the moderator. So again, we want to ignore the chi-square statistic and p-value and look at the 95% intervals. So just looking at the point estimates, we can see that the indirect effect is stronger at low levels of the moderator, and it's weaker, closer to 0, when the moderator is high. So that tells us essentially that the intervention is most salient for students with low baseline scores, and the intervention effect via self-efficacy is weaker for students with high baseline achievement. Looking at the credible intervals, we can see that the indirect effect is significant for students with low baseline scores, but it's not significant. The interval includes 0 for students with high baseline math scores. Okay, so that wraps up our quick tour of mediation and path modeling in Blimp. There's all sorts of other models we can fit. We could have latent variables, multi-level data, all different types of outcomes. So in the graphical interface, if you look at the help menu and then choose the help option, you'll find our user guide, and there are dedicated chapters with numerous examples of path models and latent variable models. Thanks again for tuning in. I hope you check out other videos.